That's true. That's true. All right, ladies and gentlemen, fast recording started. So, over the past couple days, we've been talking about energy and work and the relationship between work and energy. And right at the end of class yesterday, we were talking about this car skidding to a stop and the fact that it's negative work and that equals the change in the energy. And I just did this little calculation here that arrives at the formula that we saw in the video yesterday for how far it takes your car to stop, depending on the coefficient of friction and how fast you're going. And it all comes out of this equation, right? That work is equal to the change in energy. And that's true. But I've kind of been throwing in along the way that when we do work, actually the energy of two objects will change. One object will gain energy and one object will lose energy. And ultimately, we'll end up with the same total amount of energy, just shifted around. And that's key concept when we look at analyzing the interaction between particles, and that leads us to conservation of energy, which I'm hoping is something you guys have heard before, yes, right? When we talk about conservation, right, what's true about a substance or a quantity that is conserved? Kind of. It can't be destroyed, also can't be created. So the total amount always remains the same. We may break it up in different ways, but the total amount remains the same. Cindy, what we're thinking of a lot of times when we talk about conservation, we talk about, like, you know, saving animals or saving the rainforest or something. Yes, but right there, it's not so much getting more of something, it's preserving, keeping it the same, at least for starters. Ultimately, we want more gorillas to be in the world and stuff like that, you know. But, so.
You said you were like afraid of a rabbit because you touched him and you wanted to be scary or something.
Oh yeah, I'm like giving you so much information. I'm like, yeah. You need to like forget some of this stuff.
It's so funny.
And honestly, Cindy, I'm kind of the same way. That's the reason I don't really like biology.
Like, you touch it, it's
yeah, and it like warm,
oh my God,
and it like
why?
moves, like.
I know, I hate it.
Why? It's living, okay?
Yeah.
That's why it's so
I just
Yeah.
hate it.
It's it.
No, I
Yeah.
don't like it.
And that's one of the reasons I don't teach biology. So.
Well, I like biology. I just don't like it.
I'll
when
tell
it's
Mr. Hodge
boring.
that.
That's fine. You can tell him. So.
I don't like
He knows I don't. Yeah, like humans, okay. Like my kids, I'm okay. You know. But yeah, like
Animals,
rabbits, like
furry.
yeah.
Ew, I don't like it. Thank you so much.
So. All right. So. Okay. Right. This idea of conservation is one of the key components. Sorry, not components. One of the key foundational ideas, like I said, that goes into analyzing interaction between particles. No matter what the process, the total amount of energy in the universe remains the same, and we refer to this as conservation of energy. Now, that's the total amount of energy in the universe. When we do work, we transfer that energy around from one object to another or from one place to another, but in the end, the total amount of energy remains the same. Okay? Now, in special situations, we will see conservation of a specific type of energy, and that type of energy is mechanical energy. Hopefully you remember, I kind of mentioned it a couple days ago. Mechanical energy is the sum of potential and kinetic. Okay? So when we look at mechanical energy, it's potential plus kinetic. I wish this was a little bit more detailed, because when we talk about potential, I should go a different color for that. When we talk about potential, we actually talked about two types of potential energy, right? We talked about potential energy gravitational, and we also talked about potential energy elastic, okay? Both of those types fall into this category. So when we're talking about mechanical energy, it's these two plus kinetic energy, right? The combination of these three is mechanical energy. Okay? Good there? Now, under certain circumstances, we will see that specifically mechanical energy can be conserved. And those circumstances, as this book describes it, is in an ideal system with no form of friction. Okay? On Earth, we don't encounter this very often, right? We always have to deal with, well, I shouldn't say always, almost always, we have to deal with some form of friction, either contact friction from surfaces or air friction as we move through the atmosphere, right? We don't encounter this very often, but if we can get to the point where there is no friction acting on an object, we will see that energy is transformed from potential to kinetic or vice versa, but the sum remains constant. We generally think of it in this situation, which you have a picture of down at the bottom, okay? If we drop this set of keys from the hand down to the ground, right? Back in the very first physics unit we did, back in kinematics, we discussed that when we drop something, what is the initial velocity of that object at the moment that we drop it? We let it go. What's the initial velocity at that moment we let it go? 0. So, if the initial velocity is 0, it has no kinetic energy at the moment we let it go. But it's still up in the air, so it will have gravitational potential energy, right? MgH. We all know that what's going to happen to these keys after they're let go. They're going to drop, right? And we learned that they're going to fall under the influence of what? Gravity. What happens to things as they fall under the influence of gravity? They accelerate. In this case, they're getting faster and faster and faster, right? If they're falling just straight down. As they're going faster and faster and faster, what's happening to the kinetic energy of that object? It's increasing, but at the expense of what? As it goes faster and faster and faster, what happens to its height? It gets lower and lower and lower. So kinetic energy is increasing because it's going faster, but its gravitational potential energy is decreasing because it's getting lower and lower and lower. Right before we hit the ground, we see a complete reversal of those two. When it's at ground level, its height is 0. Right? So it has no gravitational potential energy. But it's going very, very fast. The instant before it hits the ground. That's the important part. Okay? Because once the ground acts on it, now work is being done. That's a force. Okay? The reason why it doesn't happen from here to here is because what is the only force affecting the motion of that object? Gravity, as long as we can get rid of air resistance, right? So, gravity is something that we refer to as a conservative force. Okay? Conservative forces don't change the amount of energy, I should say, don't change the amount of mechanical energy. They just convert one form of mechanical energy into another form of mechanical energy. But they won't change the amount of energy. Okay? Good there. So, the next thing you have at the top of your next page, I believe, is a picture of this lady falling out of a building. Yes? Okay. It didn't show up particularly clear over here. I think it's actually clearer on your guys' picture, but all right. So, this lady up here at the top has reached a desperate situation. There's a fire in the building. Apparently her escape route is compromised, and she feels her only option is to jump from the building. That's her purse, okay? But I would like to notice that this drawing is physically accurate, because what do you see about her purse and her?
Oh, the person's falling slower than her.
Right? It's right here, and then it's right here, and then it's right here, right? You know? So her purse is falling at the same rate as her because
Gravity acts on the same.
gravity causes the same acceleration to all objects, right? All right. Say again. No, it's not. It does, though it does like come off that way, kind of. But
Well, no one jumped off at first.
I don't know. I
So
mean,
you
yeah,
drop
so.
a heavy, can you drop a rock? Like a heavier rock that's going to land on the ground?
It was like 2 chapters ago. Yes.
Yeah, I
As long as what?
air resistance.
Right. As long as there's no air resistance,
Yeah,
right?
I
Okay.
know that. You're taller than
So,
me.
good. I'm glad you got that on recording, because so I can tell that to the people at IB. Be like, look, I taught them this. I don't know why they got this question wrong. All right, I'm gonna move the recording device out of the way. If my pen turned off. Let me move this out of the way. Come on.
It's so funny. Your face expression was so funny.
Wish I could have got that on recording.
I know,
So-
right?
All right, so this picture, in a hopefully different fashion than what happened at 9/11, there are some brave firefighters, could still be a 9/11 reference, but down here at the bottom, they have this nice, cushiony paired trampoline or whatever for her to fall into, right? So this picture, whenever I use this picture in class, which is usually a couple times a year between this class and physical science, I always think of 2 things. So one, this little trampoline thing that these firefighters have. No firefighters would actually use that nowadays, right? They have a big hook and ladder truck that they would just put the ladder up there and hopefully have her climb into the bucket and they would bring her down, right? But I wonder if at the fire station they still have that thing, that big thing up in the attic or something like that. And every spring they're like, we got to throw this thing out. And somebody's like, one guy's like, no, what if the truck's broken and we have to, okay, fine, put it back up there, right? So, but the other thing that it makes me think of is the best day of elementary school gym class, right?
Well,
Oh,
that's
yeah.
awesome.
Man,
I'll
when you
do that.
when you walked into the gym and the parachute was on the floor, yeah, buddy, that was the best day ever, right? You played the popcorn game, right? Where a bunch of people shook it and you threw the Nerf balls in and you had to catch it before it hit the ground. And then you made the mushroom, right? Everybody flips it up real high, and then you all turn
You
around.
remember that.
Because it was the best day of elementary. We had parachutes when I was in elementary
I
school.
remember that too.
So
It was fun.
I mean, I know it's hard to believe that we actually knew about physics when I was younger, but so I mean, there's got to be one here in the school, I would imagine. But yeah. Go ahead.
Is it recording right now?
I am recording right now, so choose your words carefully. So.
I was just gonna say, you continued recording and then you kind of just randomly made a 9/11 comparison. So just kind of like you're just randomly comparing things.
Yeah, Mahan made the 9/11 comparison. So,
Well,
but
no,
I mean
you,
this.
started recording, you're like, okay.
This, I mean,
9/11.
but this, unfortunately, this is a scene that does bring up 9/11 memories for some people because it's a pretty memorable. It's, yeah. I mean,
Wait, you went
but
though,
it also though what's actually kind of scary though, and I realized this year that the freshmen, most of them weren't even born
I know. It's you're so.
because it was 14 years ago.
Yeah.
And that's scary because to me it's like it was yesterday, but for you guys, like I said, you were what? Yeah, you were 3 years old or 2 years old. You don't remember it, so which is kind of weird. But I suppose in the same way, that's how my grandparents felt about Pearl Harbor. To me, Pearl Harbor is something I read about in a book. But that's
One day that
James. Go ahead. I think it's probably a trampoline might stretch a little bit too much, right? It might be something maybe like a bed sheet or something. It would bounce her back up. Now, I guess from that instance we can kind of use that comparison, right? If there was no air resistance here, and if this parachute was friction free, like a completely perfect trampoline. Sorry, I should have said trampoline. If it was completely perfect trampoline, what would happen to her? Not halfway back up.
all the way back up.
If there is no loss of this energy, right? On the way down, and this is where I was going with this, right? On the way down, what happens to her kinetic energy?
So it's just endlessly keep.
It increases, right? But as we we discussed the past couple days, how are speed and kinetic energy related to one another? Not direct.
Inverse?
They're quadratically related to one another. So, if we were to draw the kinetic energy, she starts with 0 kinetic energy up at the top, right? And then that kinetic energy goes up and up and up, but it's not a direct relationship, right? So what would it look like? Quadratic relationships look like what on graphs? They look like parabolas, right? So her kinetic energy would go up like this. Okay? Sure. All right, and so green is kinetic energy. Oh, actually, use green. Okay. All right, good there. But what happens as kinetic energy increases? What type of potential energy? Gravitational, right? So I will use blue for gravitational potential energy. But if there is no air resistance, right, what has to happen to the potential energy graph along with the kinetic energy graph? They have to be what of each other? They have to be inverses of each other, right? They have to be mirror images of one another. So potential energy starts at a very high level, but then goes down. Okay? But, James, since you brought it up, let's continue this discussion. This would get us how far in her trip? To the bottom, right before she hits the trampoline. Okay? There's a third type of mechanical energy that we introduced a little bit ago, right? What's the third type of mechanical energy that we have to consider? Elastic. Elastic potential energy only occurs when things do what? Stretch. Is there anything stretched on her trip all the way to the bottom? There isn't. So, if we use red for potential elastic energy, right, the whole time, that would be here, right? Yes? Okay. Until she hits the trampoline, right? But, you guys have been on a trampoline before, okay? Sometimes it does, you know.
I jump and then it hits my foot before I'm ready to be hit.
Yeah. Especially if there's more than one person on the trampoline. Yeah. That can actually be really dangerous. Like you can get some pretty severe injuries from the trampoline. But my point was, how long does it take you to bounce on the trampoline? Compared to like how long you're in the air.
Oh, not
You gotta go down first, right? And then you gotta go back up. But time-wise, that doesn't take very long, right? Okay? So, here, when she reaches the trampoline, right, she does go down a little bit further, yes? So, her potential energy, gravitational, would continue down to a certain point, yes? Okay? But, what's happening to her potential elastic energy during that time? It goes up, and it goes up fast, right? Because as soon as that trampoline gets stretched out, this like shoots up, right? That's not straight up, but it's a pretty steep slope, okay? What is also happening as that trampoline is stretching out? What is the trampoline there for? What is happening to the kinetic energy? The trampoline slows her down, right? Because to bounce,
oh, it's at 0 again.
it's at 0, because she has to stop before she can go back up. Does that make sense? This is way more complex than I get into with my physical science kids, just by the way. So, but then she bounces real quick. The trampoline stretches out, but when the trampoline stretches out, it goes back, right? So if it doesn't stretch anymore, what's going to happen to red? it goes down. It shoots way back down like this, right? But as the trampoline is shooting her back up in the air, potential energy starts to increase, but what else starts to increase? Kinetic increases again, and it shoots right back up to where it was. Okay? And this is the moment that she leaves the trampoline. Actually, sorry. Potential will go back up just a little bit there, because she has gone upward however far the trampoline has stretched. Does that make sense? Does this make sense so far? We doing okay? But then, once she leaves the trampoline, which way is she going? Up. What happens to things as they move in the upward direction? Let's go with what happens to their speed as in the upward direction. They slow down, right? Which means what's going to happen to her kinetic energy? It's going to go down as well, right? But if it went up as a parabola, guess what? It's going to go down as a parabola as well. But as her kinetic energy is decreasing, which potential energy? Gravitational potential energy is increasing, right? And elastic, right? Once she leaves the trampoline, is the trampoline stretched out anymore? So it just goes back to being what? It goes back to being 0. Does that make sense? Okay. But, let's see how well I did here. Okay, come on, moment of truth. We'll go purple for this one. Wait. No. Not too bad, if I do say so myself. Okay. What's the purple represent? Total what?
Oh, energy is conserved.
Total mechanical energy, right? So the purple will represent the total mechanical energy. What do we see the whole time with the purple line? It's always what? It's always high, but it's always the same. It's always the maximum, right? Here, right, potential energy, gravitational is equal to the mechanical energy because it's the only kind of mechanical energy she has right when she leaves, right? Then, as that goes down, green goes up, right? But then, when red's at its highest, blue and green are at their lowest, right? And then, if we added up blue, red, and green the entire time, we'd get purple. Does that make sense? Go ahead, Austin.
So mechanical isn't just potential plus kinetic, it's all energy.
Well, it's potential plus kinetic, but there are two types of potential energy that we have to consider. The elastic potential energy and the gravitational potential energy, right? But the whole time, remember, mechanical energy is a sum. So if we added up the values of each of these things at any individual point, we would get the purple line, okay? But, does this happen in real life? This does not happen in real life because we can't get rid of friction, right? For instance, go to the back page. I'm going to skip it. I'm going to skip the girl on the slide.
Can you take me the slide though?
What slide?
Like
Oh, we'll do it tomorrow. How's that? Okay. All right. Here is a picture that I showed you back when we were talking about acceleration of gravity. Things go up, things go down, right? Okay. In real life, this is what the graph would look like. Okay. It's an old graph. This is from like an old data acquisition system that I had a long time ago. That's why it looks cruddy like this. Okay. So, throw the ball up, and then it comes back down. Right? So, based on that, this graph shows you 3 different types of energy. Okay? What are the three types of energy, and which one represents which type of energy? Yeah, I'm asking you, okay? Yusuf, go ahead. The top line is mechanical energy, right? So if we go, but our colors from the last graph, this top line is going to be the mechanical energy. Okay? Joe, good. Squares are pluses. Squares is kinetic energy, right? I use green for kinetic energy. So this is kinetic energy. Okay? And then that means pluses probably are going to be what? Which potential? Gravitational. Because there is no elastic potential energy in this one. All right? So this is... This is energy, potential, or gravitational. This is mechanical energy. And then this is kinetic energy. Okay? First, let's make sure we understand why we know all the things of that, right? Why is the green, Joe, why did you say the green was kinetic energy? It's lower. Also, what happens to the kinetic energy initially on the up trip of this ball? What happens to the kinetic energy on the up trip? It decreases. When the ball hits the top of its motion, what is its velocity? 0. So what's the kinetic energy at this point right here? 0, right? And then, on the way back down, it speeds up again. Yes? Okay? Potential. As it goes up, what happens to the potential gravitational energy? It's at its highest point, right? And then it comes back down. Does it ever get to 0, though? Because where would it have to go to get to 0? The ground. And if you throw a ball up in the air and then catch it here, it never gets to the ground, right? Does that make sense? Then, purple, mechanical energy. But this graph is different than the graph that I just drew for the lady falling out of the building, right? How is it different? There's no trampoline, yes, okay. What's different about the mechanical energy in this picture? It's not constant. It's continuously decreasing. So is mechanical energy conserved in this graph? It is not. This is real life. Mechanical energy is not conserved. But the very first thing that we talked about today was that energy as a whole must be conserved. So if the mechanical energy is decreasing, what else has to be happening somewhere? Say again? Air resistance is a force. It's not energy. So air resistance is doing work. But if the mechanical energy of this object is decreasing, what has to be happening somewhere else? Something else or some other kind of energy is increasing. Right? So, when we talk about friction, and air resistance is a form of friction, right? When friction acts on stuff, it makes things get hotter, right? Take your hands and rub them together like this, right? What happens to your hands? They get warmer, right? So, here is a pretty famous demonstration, a pretty famous physics demonstration, and maybe tomorrow, if I remember, I'll show you a video of it because I don't have the thing to do it right here. So here's this is a pendulum, okay? And if you want to make it like really intense, you make your pendulum out of a bowling ball, okay? A pendulum. Yeah, yeah. Okay, so this is a pendulum, and like I said, if you want to be dramatic about it, you make your pendulum out of a bowling ball. So this is what you do. You get some poor unsuspecting student, and you tell them, okay, hold the bowling ball pendulum up to your face, and let it go. It swings across.
There's a pass that, you know the ball where you do that and then it like pushes it from the other side, or there's like ball,
Yeah.
ball. I have that in my house.
Next unit, we'll talk about that. So,
You want me to bring it?
I have one actually.
Oh, you have.
So, you get some poor unsuspecting student. You tell them, hold the bowling ball up to your nose. Let the bowling ball go. It goes down, and it comes back towards their face. And then they flinch because there's a bowling ball coming at their face. Right? But it will not hit them. Okay? It took me about, 4 or 5 times before I didn't flinch. Right? Because it's scary. There's a bowling ball coming at your face. So, But this graph on the left is very similar to the graph that we just saw for the ball being thrown up in the air, right? But it represents this pendulum. As we let the pendulum go, gravitational potential energy is very high, and kinetic energy is very low, because right when you let it go, it's not moving. But then as it swings downward, kinetic energy increases because it goes faster and faster and faster, and potential energy decreases because it gets lower and lower and lower until it gets to the bottom of its swing, right? This is the very bottom of this pendulum swing, right? That gets it to like right there. Oh. Okay? But once it passes through the lowest point, what starts happening? It starts heading back upward, right? So gravitational potential increases, but kinetic energy then decreases again. And on the other side, once it gets here, it has to stop. Because what is it going to do then? It's going to turn around, right? When things change directions, they have to stop before they go back the other direction. So no kinetic energy at the other side, lots of potential energy. But does it have as much potential energy as it did on the previous side? Not according to this graph. Why not? Because what's been acting on it the whole time? Air resistance. There's also probably some friction up here at the top where the string is flowing. Okay, Devin, go ahead. It does, but it's not significant enough really to to feel it. Although, if we were to let this pendulum swing back and forth, back and forth, back and forth, right? If you've ever if you take a rope and string it back and forth like this on your leg or something like that, you ever gotten like a rope burn before? That's what's happening, right? That the mechanical energy of the rope moving is being turned into heat energy, and that can give you a rope burn, right? That energy is being transferred to your skin that way, okay? All right, but not as much as there was before. I'm not sure what this is right here. I think I made it by accident, yes, okay. All right, bell's gonna ring. We'll finish up this picture. We'll do some of those calculations tomorrow. I think we're gonna push lab to next week, all right? So we can finish up this idea.